Okay. Can everyone see my screen as well? Okay, awesome. So today we're going to be talking about zero downtime operating system patching. My name is Paulo Almeida. I work at AWS. In the past, I was honored to be able to give other presentations to you, which was really great. So thanks for allowing me to come back. This is the agenda for today. I'm going to talk about how patching came to be a thing, which problems they do solve, and which problems they do not solve, but not everyone know. Which AWS services you can use to achieve zero downtime operating system patching, some of the patching strategies that we use internally as well. And if I do not speak for a long time, that means that we can have a Q&A session. But if I do speak for a long time, you can always send me your questions via email. So how patching came to be a thing. So a long time ago, like around 1940s, the idea of patching was first conceived because we had punch card programs, or tape programs as people used to call, and then at some point they would not behave as we expect. So the supplier would go back to you with a manual with instructions of, this is the band-aid or the patch that I want you to apply on a specific sheet number and also at a specific line. So this would correct the program's behavior. Of what we have is a little bit different from that, but we still inherit the terminology, but a lot of things remain the same. So for instance, although we do not have sheet numbers, we have file names, and the whole concept of columns and rows remain the same. But there is one thing that changed significantly. In the past, because for obvious reasons, we didn't have computers connected to the internet, most patches were just to fix behavioral bugs. But nowadays, most computers are connected to the internet, so even though we still do the same thing, we do that because of security vulnerabilities. This is not to say that we do not make deployments to fix bugs, but as humans and as teams, we have evolved to the point that in the ideal world, we have a very comprehensive test suite to catch most of the bugs, if not all of them. And then, unless this is really detrimental for our application, we can wait until the next deployment window. There are exceptions, of course. That's why people have hot fixes and everything. But in most cases, people can do without having the perfect behavior for a program. Now, the way we apply patches also changed a little bit. So because computers are connected to the internet, we can always just run your favorite package management tool update command, get a list of everything that's available for you, and then you can choose whether or not you want to apply those. Sounds easy, but most importantly, it sounds like all the problems are solved. And technically it's not. There are a couple of things which is not solved. But for you to understand that, I have to dive a little bit deeper into the primitives of a computer, but this will have to be an oversimplified version of it. So hang in there. So this is the primitives that we have on our computer. We have the CPU, we have the RAM. In theory, we have the hard disk, but this is exposed via a file system. And to glue all of those things together, we have the operating system, which takes hold of all of those resources. Now, when you ask your operating system to execute a program, what you're actually saying is, operating system, please load the executable file and push that to the memory. So this is roughly how it works. And then, because you have more programs to run than you have CPU cores, this program is put on a queue that the CPU eventually will get to and give that program a chance to run. So when that happens, the CPU will look at the memory, fetch preemptively lots of lines from your piece of code, which are in machine code, and start executing it. So this is the interesting thing. When you apply a patch via yum, DNF, npm, you choose your poison at that point. When you apply a patch, you are changing the file at the file system level. The program which has been already loaded into memory is not changed. So if there is any vulnerability to be exploited, unless you can guarantee that that program will be loaded back into the memory, which is not the case, will be available for other people to exploit that. Now, why don't operating systems reload the program into the memory if we have mechanisms that can tell an operating system that a file has changed? And this has everything to do with reliability or security in a way. Because when you write programs, you of course define all the rules for your program, but you can also create memory that is allocated separately from your main program. And you have to keep track of those memories. If you don't, either there will be some data corruption or there will be a memory leak. In both cases, this is not good. When you change your program, the new patched version may not have everything that it needs to have in order to keep track of the previous program's memory allocation. So there isn't much we can actually do, not with the current way we run programs. This is not to say that in the future there can be something different, but once a solution gets cemented into this technology stack that we've been using since the 1960s, it's really hard to change things. Really hard, and that's one of those cases. Now, what does that mean is no reboot means no patch, because the only way you can guarantee that you're running the latest version of your program is by taking everything down, rebooting your machine, and then starting them back up. One example would be your program and mine might be using a common shared library. In that particular case, that shared library, if that one gets updated and I take down my program, but your program doesn't take down, there will be two versions in memory. One of them will be available to be exploited. So the only way you can do this safely is by rebooting the machine. So no reboot means no patch. Plain and simple. And if anyone tells you otherwise, that person either is lying or is trying to sell you something. Do not fall for that trap. Now, I know that we have a very smart audience, and I'm pretty sure that at least a couple of you will be thinking something like, hang on, I've heard of kernel live patching. So are you trying to imply that they are lying? And the answer would be yes and no at the same time. So let's start from the beginning. So kernel live patching is a technology that allows sysadmins or users per se to apply patches to a running operating system without rebooting, which almost cancels what I just said. But there are very important differences. So the program that you and I write do not run in kernel space. They run in user space because they are business application. We do everything within our power to make sure that our application doesn't have any sort of connectivity to any other application unless we say so. We tend to isolate applications. But kernel space, which is the operating system per se, is the program that is actually running all of the other user space programs. So it has access to everything. It's a different can of worms. And in that particular case, you can, in a very specific way, you can have patches without rebooting. And I'll dig deeper into that. But first of all, understand that applying a patch to the operating system is not the same as applying a patch to the library that became vulnerable. Those are two different things. Both of them have to be patched, but they are two different things. Now, the way you apply kernel life patches nowadays are very, very convenient because it looks like and it feels like you are you're installing a regular program because you still use your package management tool of choice, right? So what happens behind the scenes is the following. If you ever dug deeper into RPM package format or Debian package format, you would notice that they have one thing called scriptlets. So scriptlets are pieces of code that can run before a program is installed and after the program is installed. In theory, and in the ideal world, that was for checking for compatibility before you install the package, but also to do some configuration after the program is installed. For instance, if you install Apache, in the scriptlet, there will be a couple of instructions that run in shell script that will try to create a service and start the service for you. So when you reboot your machine, the service will be up and running again. So this is the mechanism, but they use those scriptless mechanism to interface with the operating system and say, this is the patch, this is our old instruction that need to run in order for that to be the thing. Now, the example I'm showing you right now shows you how to apply kernel life patches for everything that's available. Maybe you're not interested in everything that's available. Maybe you're just concerned about one particular vulnerability. And in order to do that, you can also filter that by the CVE ID, which is how the way we define and catalog vulnerabilities that are well known to public. Just a disclaimer. The next slide is going to be the hardest one, but if you make it through the next slide, then everything will make sense. Okay? Hang in there. You're doing great, by the way. How kernel patching works behind the scenes. So let's focus on the left-hand side. Old function is the unpatched version. Okay? So I'm just looking at the left-hand side here. At the top, there is this little thing called NOOP, which stands for non-operational instructions. The way that kernel life patching works is, first, it forces you to compile your entire operating system differently because it will inject at the top of every single function a buffer zone of NOOP instructions, which are instructions that do not change the state of your program, so it's not going to interfere with the logic your program is doing, but they are there should you need it. And the way it will work once you patch is the following. Those NOOP instructions will check two different technologies, which is beyond the scope of this conversation for simplicity's argument, but essentially one of them is the kernel life patch engine. That thing here on the left-hand side, the kgraph thing, will do the following decision. We'll make the following decision. If the patched version is already applied and is in memory, that means that we have a new version to be executed. So instead of returning back to the old function and execute everything that was in there before, it will redirect that function to the new function. So all the references to the previous functions will remain intact, which is great, and your operating system will run the new function. Now, because now you know how that works, we can infer things that not a lot of people will tell you up front because it's not good for them. So thing number one, this jump between calls means that your CPU cache has to be invalidated. So kernel life patching has a performance overhead, and that implies on whether or not that can be applicable for your use case. Not a lot of people like to talk about it, but it can't. There are functions in the kernel that execute once every 10 microseconds. If you patch that function, the slowdown will be massive. Fortunately, that's not the most common case, but it's a possibility. The other thing is, being developers, most of you, you understand that if you call a function and that function requires 3 parameters, all of them integer, for instance, you know that if you do not recompile your program and all the references are kept the same, you have to comply with the method signature, which means where it's located at, as well as all the parameters it's expecting. That implies that not all vulnerabilities can be patched using kernel life patch, because if the patch requires external information which is not available in the context of that function, and you cannot fetch that from elsewhere, then that means you cannot find what you need in order to choose whether or not the program should be doing what it does. No, people are not upfront about it, so now you know one more thing. Cool. When it comes to the availability of kernel life patching, all major Linux distributions offer that for you, for a cost, of course. And the cost makes perfect sense, because for someone to provide you with a life patch, they have to craft the life patch first. And not a lot of companies are willing to hire a kernel engineer. And that was really sad for me, but that's a different discussion. Now, apart from that, they have to test that patch in a plethora of different types of hardware, and that takes time. So the cost you pay for a kernel life patch support tier on one of those distributions are actually quite cost effective. So I'm not complaining about it. Now, Amazon Linux provides you with kernel life patching for free. So if you needed one more reason why you should use Amazon Linux, then here it is. But it also comes with some fine prints, and I want to discuss them with you. It must be enabled because it does not come enabled by default. And this is really intriguing. I'm not sure how many of you have worked with low-level development, but there is one thing which is very interesting about low-level development. There is no try-catch in kernel. If something is outside of the expected range of parameters, you have 2 choices you can make. Either you let that go and allow that error to be propagated to maybe to the disk or to the memory, which can lead to a security vulnerability or data corruption permanently, which is no good, or your operating system can die to maintain integrity. And that's the choice that most low-level developers make. They actually add assert statements in their code saying, if this is outside of what I think this function can handle, it's your mission to die, and print a crash dump that will allow other people to debug it with as much information as you can possibly give, right? Second thing, because there is a risk when applying patches, given the fact that there is no try-catch, that risk also implies that if you have a vulnerability which has a low priority, then it's not worth the risk. So all the patches that Amazon will provide you with, they are for CV scoring system 7 or higher, which means high vulnerability or critical vulnerability. So in that case, it kind of makes a little bit more sense. Third one, and that's my favorite paragraph from the documentation. It tells you exactly what kernel life patching is for. I will read it out for you. AWS provides kernel life patches for an Amazon Linux kernel version for up to 3 months after its release. After the 3-month period, you must update to a later kernel version to continue to receive live patches. So what we can infer out of that, if we read between the lines, what we're trying to say is Live patching is not a solution for a no reboot problem. Live patching is a solution for a delayed reboot option, and you should use that accordingly. For instance, all systems, regardless of whether they are highly available or not, they must have a maintenance window. That's paramount. Even if you don't need it, or even if you don't use it, but it's paramount. And let's say that your next maintenance window agreed with the customer is in 2 months' time. Last night, there was a 0-day vulnerability that became known, and you have to apply a patch. In that particular case, because you cannot reboot your machine without breaching a legal contract with your customer, in that particular case, kernel live patching is a good option to use. Remember, it includes overhead, and that implies that your system will run slightly slower. But in that particular case, that's the right tool for the job. Anything else is probably someone trying to mutilate or misuse the technology. So don't fall for that trap. Which AWS services can we use to achieve zero downtime operating system functionally wise? Because in theory we can't do it, but functionally wise we can do it. And by functionally I mean we can patch systems without having our customers impacted. So that can be broken down into 2 different categories of services that are at your disposal. I'm not listing all of them in the best interest of time, of course, but if you have an interesting use case or something that I haven't mentioned here, by all means talk to me or to your account and say I'm pretty sure they're going to be happy to talk to you about it. But the 2 categories of services are the AMI creation or the operating system update and the deployment tools. So for the AMI creation, one service that we have is called EC2 Image Builder. So if you haven't used that, the sales elevator pitch would be the following. You can define in YAML files all the things you want to be installed in a particular machine, and you can also define testings to make sure that the things that are installed are properly configured. Okay, and then you can distribute those golden images across your AWS account. Couple of highlights. So highlight number 1, that's free, which is great. I like free things, and I'm assuming that all of us do. The only thing you're going to pay for is the storage used for the machine snapshot that is created, but you're not paying for the execution and the installation of those things. And some machines can actually take quite a while to configure, even using automation. It supports reusable recipes for both installation and testing components. We cannot argue that this is a bad thing. Reusable means we can save time in the future. Great point. Now, this is my personal favorite. It can output the image format in different formats other than the one that AWS has, such as VHDX, VMDK, and OVF. Now, you do not need to know all of those formats, but the last one, OVF, stands for Open Virtualization Format. What it means is that you can take this open source standard and run that in other places, both locally, different cloud providers, and that commitment to abide to open source standards is something that I highly value, right? And I'm assuming that most people do as well. And one complaint is, because that's a feature, not an actual fully managed services, it does not have a logo. I've been complaining about it with other people, but yeah, it doesn't have any logo. So when you have to put that in your architectural diagram, that's a little bit tough. Now, deployment tools. Deployment tool is a very hot topic because people love to have strong opinions on how things should be deployed. And I'm not here to just say you shouldn't be using what you do. I'm aware that in the past, people were crazy about Terraform. Some people still are crazy about Terraform. Me personally, I love it. But I know that a lot of companies have moved towards either CDK or Pulumi, which are different ways of defining your infrastructure state using imperative programming style. Now, there is one thing that I want you to know, but there is a disclaimer first. You don't have to change what you do. I'm just saying that for that particular piece of the automation, CloudFormation can be useful because CloudFormation has one behavior that none of the other tools give you the same behavior out of the box, which is if you have a stack which is deployed in CloudFormation and you try to make an update to that stack and something goes wrong, it rolls back to the previous working state. And this is great because let's take into consideration Terraform. When you try to apply a change in your Terraform code and that fails, it simply tells you, I failed. And it's your mission to figure out how to fix it. But depending on the change you're trying to make, you can take the whole application down. But in the case of the CloudFormation, you can configure that and fine-tune that in a way that it will deploy the machines without impacting your existing customers, and if anything goes wrong, it will replace it back with the old unpatched machine that was previously running. This is roughly how it works. It's a very summarized way I can share with you over email later, but essentially I just have two parameters: the instance type, which is the hardware that your operating system will run against, and what is the AMI version, which is the ID of that operating system image that we created with our software, okay? And then in this CloudFormation template, I only defined two resources. So all of my infrastructure is actually using, in this case, is using Terraform. I'm actually connecting Terraform to CloudFormation just for that. The only two resources I have are the launch configuration, which most people nowadays use launch template, so it wouldn't change the behavior, but at the time that I wrote that, I was using launch configuration, and the auto scaling group. So the launch configuration is a recipe that contains which machines and which hardware your auto scaling group will follow when it needs to scale or shrink the number of machines within your cluster. Now, this is the meat of that strategy. There is one, if you take a look at the update policy and you see, the harmony between the parameters, you will understand what it's trying to do. So I defined that the update policy would be rolling update, and I'm also saying the following: the minimum amount of instances in service that your application must have is 1. So at no point all the machines will be taken down altogether and your customer will not be able to access it. The other thing I'm saying is the max batch size, which is how many instances you will update that at once, is 1. Also, if you have a different number of architecture with a different number of services or machines, you may tweak those numbers. They are not absolute, but it gives you the idea of how that can work. And the other two things which are relevant is the pause time, which is I want the auto scaling group to have a cooldown period of 15 minutes that will give the auto scaling group and also your application, your SysOps or site reliability engineer team an opportunity for, first, wait for the application to be booted. Second, and in this moment the most important part, to be able to evaluate if the machine or if the program, if the application is behaving the way we expect it. And we're assuming that your observability practice is up to date in order for you to obtain that information. Last but not least, I'm also suspending some of the processes that can interfere with the auto scaling deployment. So, for instance, I'm disabling the health check of the auto scaling group. I'm saying while the application is booting, Of course, you're trying to check whether or not the machine is healthy or not. But the application needs some time before it can fully boot up. And when it does, then you can evaluate whether we have to replace that instance with a healthy one or not. So it's the combination of those four parameters that I want you to have a play with. Now, let's put everything together and see how that works. And then I will talk to you about stateful workloads, which we have to do a couple of things different in order to achieve that. So for stateless workloads, let's assume first what we have. So we have a patched application or patched AMI. We have a way to trigger a deployment. There are many ways people use it today. So it could be either Jenkins, it could be code pipeline. It really doesn't matter as long as you can trigger CloudFormation, that's enough. We have CloudFormation, which is the part which is orchestrating the whole deployment. And in our application, we have the following. We have the old launch template, which is the recipe, as I mentioned. We have the old scaling group, which contains 2 different machines. Those machines are connected to a load balancer, which is serving content to the customer at the top right hand side. Now, what will happen first is the following. So CloudFormation will create a new launch template. So at some point we're going to have 2, and it will associate that launch template with the old scaling group. The auto scaling group, given the update policy that we defined, will try to do the following. It will try to replace a single instance, and it will wait for a signal, which is a HTTP request, to be sent back to CloudFormation, signaling that this machine is now up and running. Now, there are 2 possible outcomes here. It can either succeed or fail, right? But if that fails, the rollback process will basically do the following. It still have access to your old launch template. So it will delete your new launch template and replace your new instance, quote unquote, the buggy one, with the old EC2 instance, which was working before. So that's the type of peace of mind you may want to have. Now, in the other outcome, which is the deployment succeeded and that new instance passed the health checks and everything, then it will move on after the cooldown period to the other instance. And because the load balancer is aware of which one of those instances have been registered or deregistered, from a customer perspective, in the case of stateless workloads, they will not perceive that the application is being patched or replaced with a new patched operating system. So functionally wise, that's almost like a zero downtime patch. But in practice, we know the limitations as we discussed that just a while ago. Now, what about stateful workloads? And I love that question because as much as I love statefulness, we live in a world that is full of state. And not a lot of people realize this, but in order for your application to be stateless, somebody else's application has to be stateful because they need to persist your state. And this is fine when you have such a very small application. You just have like a couple of EC2 that push that data to a different database, whether that's Dynamo or RDS, and you think like, okay, that's all good. I just want a fully managed service. That's all. But as your organization gets bigger, it's more and more common for you to have a plethora of different microsystems that are part of your entire greater picture. And everyone will try to push the state to somebody else's application. So statefulness, it's a thing, and you can push the responsibility to a different team, but that does not mean you'll make it easy for the other team. So striking that balance is a very tricky thing to do. But still, because we have stateful workloads, we know that this is substantially harder for obvious reasons. You have to keep track of of the data that you received. And by keeping track of that data and being able to make sure that this is available when the new instance is launched, you have to replicate data. Physically speaking and mathematically speaking, there is no other way. There are two types of replication that most people know. It's either asynchronous, which means it will happen at some point, or synchronous, which will happen right now. Asynchronous creates a big problem because as much as we want these two machines to be synchronized, there is a chance that your latest data won't have been replicated when you take the primary machine down. So the only guarantee that you have is that I'm going to lose data. But the opposite is actually not ideal either, because when you have synchronous replication, that limits the amount of instances you can have because that's a linear problem. If you have 3 instances you have to replicate to every time you receive a transaction, it means you have to wait for 3 different acknowledgements before you send the response back to your user. Mathematically speaking, this will limit the performance of your system. So it's a very interesting thing. But we know that asynchronous is not an option. That's the most important part. Now, I see some people erroneously using RPO, which is recovery point objective, and RTO, recovery time objective, to justify the use of asynchronous replication. Because they say, look, if we lose data, that's part of our deal. We can lose data as long as the amount of data we lose is really small. I disagree with that categorically, because RTO and RPO are designed and defined for disaster recovery situations. This is not for operational management situations. This is something that has to be common. Your customer is not going to be happy if you keep losing data once every week, right? So even though you can legally get away from it with murder in this case, my suggestion is don't use that strategy. Let's find a better strategy, okay? So I cannot tell you how we do things internally at Amazon with all the details that I would love to share with you, but I can share with you the way we solve the statefulness problem for RDS, and then that will probably give you an idea of how that can be applicable for other stateful environments. So in the case of RDS, if you're using multi-AZ, of course, you have a single endpoint, which is a DNS entry, which is pointing to the active instance. Some people have doubts about, is this synchronous replication or asynchronous? Because database engines are well known for asynchronous replication. So it becomes kind of like intuitive. But this is not what we do. We replicate things in a synchronous manner by replicating the data at the hard disk level. So when we do that, first we make the database freer, so it doesn't have to spend resources replicating the data, which is great. We do that for you. And the second thing is the replication lag between those 2 instances tend to be 0. It can always go wrong, and we know how physics work, but it tends to be 0 99% of the time. Now, this is roughly how that works. So this is a screenshot from a presentation given in 2016 about the Aurora deep dive. I highly recommend you to watch that presentation. It was great. And then they were comparing how the replication of MySQL and Aurora works. So in this case, the primary instance would be the instance that's reading and writing data to the disk, and the replica instance would be the standby instance. When a transaction happens, the primary instance will will wait to send the response back to the user on whether the transaction has been committed or not until three things happen. First, the data is stored in a primary block disk. That primary block disk is mirrored within the same availability zone. So that's the first layer of protection that you have. And the third step is the same data that was asked to store in this first and second EPS will be replicated to a different AZ, and the same process will happen. When processes 1, 2, and 3 are acknowledged, only then you send the response back to the user saying transaction is committed. So there are certain blog posts on the AWS database blog which talk more about all the little details, and I believe you if you want, I can share that with you, and that's really, really intuitive and really interesting on how some of those things are done behind the scenes. Now, a few takeaways. So your architecture have to change depending on your security goals, because your application deployment and your security or your patching strategy must be aligned with each other. In a lot of cases, I see people doing these two different types of pipeline, but nowadays, specifically because a lot of our applications are moving towards container, you are also responsible for patching your containers, patching the dependencies that are part of your application's container. So they have to be aligned in terms of how the application would behave to support either a stateless rolling deployment or a stateful one. When it comes to the AWS tooling to support you, I mentioned some of them, but for each case, there will be different services that could be useful for you. So one that I didn't mention is the patching manager that we have, which is also part of AWS Systems Manager service. I highly recommend you to take a look at that as well. And last but not least, if I wanted anything from this presentation, is to make sure that we all agree that before making a choice of whether using one technology or another for everything that we do not make that choice lightly. We try to understand the primitives and the inner workings of a technology at a certain level so we can make a more informed decision. In the case of the kernel life patching, a lot of those companies are simply trying to make it sound magical, like you just reboot, don't patch. Those are actually words out of a marketing department from one of those companies. So try to take a look at those things. Try to figure out, where a technology is not applicable, because where a technology is applicable is usually written on a website, but the other side of the equation you have to figure out yourself. But making a more informed decision will give you peace of mind in the long term. Last but not least, thank you so much. I do have a couple of minutes if you want to ask any questions. My last ask from you is, if you can and if you want as well, scan the barcode and answer a 3 or 4 question survey. That would help me a lot internally here. So thank you so much for your time, and looking forward to the next year if you guys want to hear from me once again.
Brilliant. Thank you so much, Paulo. We'll give people some time to scan the QR code, but also, please do reach out with your questions. Just use the raise hand function, and if you're the first one in, just go off mute and ask away.
Don't be shy. Yes, Wilson?
Hi, Paulo. Yeah, thanks. I really enjoyed it. Just wondering if things like that is available for Lightsail too, like kernel life patching. So I have a bunch of Lightsail instance that potentially I want to have a look whether live patching works. Do I need to specifically create a new Lysol instance using Amazon Linux 2 and then try to see if I can opt in, or is there any other recommendations you would?
Right. So just to make sure we are on the same page, the question is kernel live patching available for light sail?
Yes.
Okay, so in that case, the answer is yes. Your light sail machine must be complying with those criteria I mentioned before. So it must be using a recent kernel version, and if that's an Amazon Linux, I think now it's the 2023. You can enable the kernel live patching and make use of the feature.
Cool. Awesome. Thanks.
Thank you. Awesome. Any other questions? Okay, that's okay if there isn't. Look, my email is being shared right now. Feel free to ping me directly or to add me on GitHub or LinkedIn. I'm always happy to have a coffee, catch up, and talk about geek stuff. So yeah, thank you so much for your time. Thanks, Fred. Thanks, Rebecca, for the opportunity. It was really nice.
Wonderful. Thank you so much, Paulo.
Thank you, Paulo.
Thank you. See you guys. Bye-bye.
Thank you. See you.